Hello everyone, I'm Shuk from Penn, here to give you a brief overview of vision transformers and their application to cosmology inference from weak lensing probes, hopefully to start off longer conversations that we can continue to have throughout the rest of this week. Setting up our problem first, weak lensing probes map matter distribution by measuring correlated distortions in the shape of background galaxies due to light bending due to foreground matter over densities. As we know, at smaller scales, gravitational collapse leads to deviations from linear growth theory, resulting in non-Gaussian information. So as a schematic on the top right here, we have a typical data product of a weak lensing survey. Here, the dark energy survey's convergence map. If I plot a simulated histogram of these kappa values, you see a higher value tail that is due to gravity at smaller scales. Essentially, this information is missed by a two-point statistic, so we need a more complicated summary statistic than that. There have been several examples ranging from, say, peak counts to CNNs to scattering transforms. We specifically explore vision transformers as a compression model. Transformers use the self-attention mechanism over sequential tokens. For a normal language processing task, it's words in a sentence. For us, it's patches from an image. We linearly project these to a lower dimensional space, add some positional embeddings to still encode some information about the ordering. All of this is fed into a transformer encoder and finally MLP just infers your favorite cosmological parameters. I'm listing here some past applications in astronomy for vision transformers. And these are sort of color coded. So I'm like pretending to be a reviewer or a salesman for a VIT. So these are color coded by how these papers think VITs compared to a conventional machine learning approach like a CNN. And the point I'm trying to get across here is your mileage might vary depending on the task or your data set. For example, sometimes VITs can infer parameters a CNN cannot, or sometimes you just get comparable or even slightly worse performance. So looking at some results from weak lensing, hence with that in mind, here I'm comparing a vision transformer to ResNet 50, which is a state-of-the-art convolutional neural net. We work with a WCDM light cone simulation using pre-trained networks, and these posteriors are constructed with LFI. Glad to talk more about these details. Reach out. I don't have enough time to delve into the depth. We see comparable or better constraints for all of our relevant parameters for weak lensing for maps with DES-like noise and sky coverage. We're now working on extending this for the Rubin Observatory, applying it to real data and validating and interpreting these results and the performance. So yeah, thank you. Thanks a lot to the organizers and the staff here. And feel free to shoot me an email or just catch me in person if you're in New York. Cheers.